Dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about laser. We'll learn about how to produce laser, the differences between normal light and laser light, the two types of emission, the one that emits laser, yes, which is stimulated emission, and spontaneous emission, which produces normal light. So let's get started. Laser. Okay, laser is light amplification by stimulated emission of radiation. It is amplification of light by stimulated emission of radiation. In 1917, Einstein showed that there are two kinds of emission: the rapid spontaneous emission and the delayed stimulated emission. The first type, as I said, it is spontaneous emission. In front of you, okay, we'll focus on spontaneous emission. Okay, here we've got an atom in which electron is found in the ground state, and we've got a certain photon, incident photon, having a certain energy, which is the difference between E1 and E2. Then what happens when this photon falls on the atom? Yes, electron is excited and it makes transition to the energy level E2, but it stays for a very short time. Then it relaxes once again to the ground state, emitting a photon having energy which is equal to E2 minus E1 equal to h nu. Okay, and don't never forget that any atom, yes, has many, yes, different energy levels. Okay, so the atom has energy levels. The lowest of these energy levels is called the ground state, and it is denoted by E1. The atom may be excited to one of higher energy levels. Let it be E2. When a photon of the appropriate amount of energy, the energy which is exactly equal to the difference between E2 and E1, falls on the atom, falls on an atom in the ground state, the atom absorbs the photon and makes transition to the excited energy level E2. The atom, after a certain time, we call this time lifetime, and it is about 10 to the power of -8 seconds, the atom, the electron in the atom, spontaneously falls out of its own accord, falls back to the ground state. And it emits a photon of energy, as I said, equal to the difference between the two energy levels, and it is equal to h nu. Your attention, the emitted photon had the same frequency and energy as the absorbed one. Your attention once again. Spontaneous emission is not triggered by an external factor, by an external influence. But the atom, after its lifetime is over, moves of its own accord to the ground state. Spontaneous emission, okay, what about it? Spontaneous emission is the common feature of the radiation emitted by the normal light sources. Let me say it again. Spontaneous emission is the common feature of the radiation emitted by the normal light sources. Spontaneous emission is defined as, so now I'm mentioning the definition of spontaneous emission. It is defined as the emission which occurs when an electron relaxes under no influence of any external factors from an excited state to its initial state after its lifetime is over, is elapsed. And what about the second type of emission, which gives, yes, laser? It is stimulated emission. Okay, in front of you we've got an atom which already excited. Okay, the atom was excited, the electron was excited. Okay, and we've got a stimulating photon passes by the excited atom. What happens? The stimulating, the stimulating photon urges the electron to relax to E1 before its lifetime is over. So we've got two photons, the stimulating photon and the stimulated one. So when a photon of the appropriate energy equal to E2 minus E1, passes by an excited atom before its lifetime is over, the photon stimulates the excited atom to fall from E2 to E1. And a photon of energy E2 minus E1, which is equal to h nu, is emitted in addition to the stimulating photon. The stimulating and stimulated photons have the same frequency, phase and direction. They have the same frequency, the same phase, and they've got the same direction. That's to say, the emitted photon is in every way identical to the stimulating photon. The photons emitted by stimulated emission are coherent. Okay, they are in phase and collimated for long distances. They are highly concentrated and remain unscattered, unlike the photons emitted by spontaneous emission. Very important piece of information: stimulated emission is the common feature of laser. Stimulated emission is the emission of a photon. This is the definition of stimulated emission. It is the emission of a photon under the effect of another, such that the emitted photon is in every way identical to the incident photon. We call it the stimulating photon. And now talking about the characteristics of the stimulated emission. The stimulated emission is characterized by the emission of a new photon in addition to the stimulating photon. Secondly, the emitted photon and the stimulating photon are in every way identical. And now let's make a comparison between spontaneous emission and stimulated emission. First of all, in a spontaneous emission, the atom is in the ground state when the incident photon falls on it. But in a stimulated emission, the atom is excited, not in the ground state. Its lifetime is not over when the stimulating photon passes by it. Okay, second point of difference. In a spontaneous emission, the atom absorbs the incident photon and makes transition to the excited energy level. In a stimulated emission, the atom, yes, does not absorb the stimulating photon. Also, the photons emitted by spontaneous emission have a wide range of wavelengths. That's why they are called polychromatic. Photons emitted by spontaneous emission are polychromatic, but photons emitted by stimulated emission, yes, are of one wavelength. They are monochromatic. The photons emitted by spontaneous emission propagate randomly in all directions. Photons emitted by stimulated emission are coherent and propagate in one direction as a collimated parallel beam. Spontaneous emission is not triggered by external influence. The excited atom falls of its own accord from the excited state to the ground state. Stimulated emission is triggered by external influence. The intensity of the photons emitted by spontaneous emission obeys the inverse square law of light. So the photons emitted have large angle of divergence, have large spreading, and they are easily scattered when colliding with the particles of the medium. But talking about stimulated emission, the intensity of the light emitted by stimulated emission, the intensity does not obey the inverse square law. That's to say, it remains constant over long distances. So the spreading effect is nil or almost nil, and limited scattering takes place. Spontaneous emission is the dominant feature, dominant radiation in ordinary light sources. Stimulated emission is the dominant radiation in laser sources. And now talking about characteristics, properties of laser. First property, which is monochromaticity. As a matter of fact, laser light has high monochromaticity. Laser light has a spectral line width, okay, spectral line with a very small bandwidth, and the intensity is concentrated at the wavelength of that spectral line. Hence, laser light is highly monochromatic. Okay, monochromaticity, we call it purity of spectrum. So we can say laser has high purity of spectrum. Unlike laser light, a selected line in an ordinary light source, such as the light emitted from a gas discharge tube, includes a wide band of wavelengths. This explains why the ordinary color appears to have different shades to the naked eye. Second property, which is collimation. Okay, we can say laser is highly collimated and it is highly directional. Okay. In ordinary light sources, the diameter of the emitted beam increases with the distance, while in laser light, the diameter stays unchanged, unaltered for long distances without much scattering, without much divergence. Thus, energy is transmitted without much loss. Okay, and we've got another property. It is coherence. Laser light is highly coherent. What does it mean? Photons of ordinary light sources propagate randomly. Okay. Photons of ordinary light sources propagate randomly, incoherently. Okay? They emanate at different instants of time and have inconsistent and varying phase. This about the normal light. In laser light, photons emanate coherently, both in time and place, since they come out together at the same time. Okay. And they maintain the same phase during propagation over long distances. This makes laser light very intense and focused light. Last property, it is about intensity. Intensity of laser. Laser light is very intense. Photons of ordinary light source obey the inverse square law, while photons of laser light do not. Their intensity remains unchanged for long distances. And now talking about theory of the laser action. Theory of the laser action. Laser action depends on driving the atoms or molecules of the active material. So, laser action depends on driving the atoms or molecules of the active material into a situation known as population inversion situation. What about it? What about this situation? In this situation, the number of atoms in the excited state is greater than the number of atoms in the ground state. The active materials, okay, amplifying material used in laser are chosen because they possess metastable energy levels, okay, metastable states. When the situation of population inversion is reached, stimulated emission becomes predominant and laser light is produced. And now let's define a metastable state. It is a state in which electrons remain excited for long time. It is 10 to the power of -3 seconds. If you compare this to the time of spontaneous emission, it was 10 to the power of negative 8, but now it is 10 to the power of negative 3. So metastable state is a state in which electrons remain excited for long time. And now talking about the main components of a laser. Despite the variations in size, type, and energy in lasers, yes, 3 common components must exist in any laser. 3 major components exist in any device that produces laser. First of all, the active medium, and it can be a crystalline solid. For example, the active medium found in ruby laser. It could be a semiconductor, for example, the one found in crystalline silicon. A liquid dye, for example, organic dyes solved in water, and gas atoms in helium neon mixture, ionized gas, for example, argon in argon laser, molecular gases, for example, carbon dioxide in carbon dioxide laser, a source of energy. Second component, second major component, there must be a source of energy to excite the active medium as follows. Excitation by electrical energy. Excitation by electrical energy, either by using radio frequency waves or using electric discharge under DC voltage, and this happens, for example, in helium neon laser, the one you should know it. Argon laser and carbon dioxide laser. Excitation by light energy. It is optical energy, which is known as optical pumping. So excitation could be by light energy, okay, and then the pumping is known as optical pumping. It occurs either by using flash tubes, a ruby laser for example, or by using a laser beam as a source of energy. By using a laser beam as a source of energy, and it happens in liquid dye laser. And we want to define, yes, pumping process. To give it a definition, what about the pumping process? It is imparting of energy to the active medium, okay, to excite it. Imparting of energy to the active medium to excite it. And also we've got thermal excitation. Okay, let me remind you something. Second component, second major component of any laser is a source of energy to excite the active material. Okay, we've got thermal excitation. In this case, a gas is strongly heated, given the molecules or the atoms sufficient kinetic energy, so that during collisions with the active material is excited. For example, in helium neon laser. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all.